Hello everyone and welcome to our channel. In last class we have talked about two coordinate system, rectangular coordinate system and 2D polar coordinate system. So today we'll talk about another two important coordinate system, or spherical polar coordinate system and cylindrical coordinate system. So we'll start with spherical polar coordinate system and then we'll talk about cylindrical coordinate system. Okay. So let's start with the spherical polar coordinate system. So just like in rectangular coordinate system, we have noticed that if we want to represent a point in rectangular coordinate system, we need three variables x, y, and z. Similarly, in spherical polar coordinate system, if we want to represent a point, we need also three variables. So what are these three variables? So to see if what are these three variables, let me draw a figure here. Let's say this is a z-axis, this is y-axis, and this is x-axis. Okay, x-axis, y-axis, and z-axis. And also, this is the origin of this coordinate system. Let's say O. It has coordinate 0, 0, 0. Now, let me also draw sphere whose center lies at the coordinates at the origin of this rectangular coordinate system. And radius of this sphere, let's say capital R. Okay. Yep. So this is a sphere whose center is at the origin of this rectangular coordinate system. Now consider a point in the space, P point, and let's say this point has coordinate in terms of rectangular coordinate, so x, y, and z. Now if we want to represent this point, same point P point, in terms of spherical polar coordinate, then we have to define three variables. What are these three variables? First, let me connect these 2 points, P point and O point. So first we have to define this length, that is the distance of this point from the origin. Okay, so in spherical polar coordinate, that distance is defined by, represented by r. This is the r. Next, what we have to define in spherical polar coordinate, what is the angle between this r and the positive z-axis? What is the angle between this r and positive z-axis? This angle represented by theta. Okay, this angle is theta. Third, since this P point in actually in space, so this r also will lies in space. So now this r we can take projection on the xy plane as well as on the z-axis. So now if we want to take projection of this r on the xy plane, let's say this is the projection length on this r on the xy plane. Then this angle between this projection length on the xy plane and the positive x-axis is represented by another angle, and this angle is called phi. Okay. Phi. So to represent this point, same point P in terms of spherical polar coordinate, we need these three variables. One, R, which will represent the distance of this point from the center of the sphere. Second, theta, which is the angle between R and positive z axis. And third coordinate is phi, which is the angle between the projection of this R on the xy plane and the positive x-axis. So in spherical polar coordinate, we can represent this point by R, theta, and phi. R, theta, and phi. Now the important point is here, this P point, if we represent in rectangular coordinate system, then we can represent x, y, z. If we represent the same point in spherical polar coordinate, we can represent this R, theta, phi. But in both the cases, we are representing the same point P with the same coordinate, same origin O. So that's mean somehow this R, theta, phi and x, y, z, they will be related with each other. So let me write first this x, y, z in terms of R, theta, phi. So to write this value of x, y, z in terms of R, theta, phi, let me remind you, I told you on the first class that we represent a point in rectangular coordinate system by x, y, z. But what this value x, y, z represent? So I told you that if this point P, and if we connect this point with the origin O, we'll get a length vector. And then if we take the projection of this length vector on the x-axis, y-axis, z-axis, that projection length actually respectively x, y, and z. So in this case, if we take the projection of this R on the x-axis, y-axis, and z-axis, that's projection length must be x, y, and z. So in order to write the value of x, y, z in terms of R, theta, phi, what we have to do? We have to take projection of this R vector on the x-axis, y-axis, and z-axis. So for that, let me first take the projection of this R on the z-axis. So for that, we can draw a perpendicular line from P point on the z-axis. So this angle is 90, and this will be the projection length of R on the z-axis. So from figure, we can write what will be this projection length. Since this angle is 90, O to P, that distance is R, and this angle is theta. So we can write this projection length will be actually R cos theta. Yeah, this projection length will be R cos theta. Now since this R is in the space, so another projection of this R will lies in the xy plane. So in this case, this is the projection on the xy plane. So what will be the length of this projection? This length. If this angle is theta, this angle will be 90 minus theta, because z-axis is perpendicular to the xy plane. So if this angle is theta, then this will be 90 minus theta. So this component will be R 90 minus theta, that's mean R sin theta. Okay. R sin theta. But in order to write the value of x, y, z in terms of R, theta, phi, we have to take the projection of R on the x-axis, y-axis, and z-axis. So to calculate the projection length of this R on the x-axis, again what we have to do, we have to take projection of this length on the x-axis and y-axis. So for that, if we draw a perpendicular from this point to on the x-axis and on the y-axis, so this length, these two length, origin to this point, and on the y-axis this point to this point. This will be the projection of r on the x-axis and y-axis. Now what will be the projection length of r on the x-axis? So already we have written this projection length is r sine theta. Now this r sine theta makes an angle phi with the positive x-axis. This angle is 90. So what will be this length? This length again it will be cos of this length. So it will be r sine theta into cos phi. R sine theta into cos phi. Now if this angle is 90, means this projection length r sine theta, if this r sine theta makes an angle phi with the positive x-axis, so what will be the angle between this r sine theta and the positive y-axis? It will be 90 minus phi. So the projection length of r sine theta on the y-axis, we can write r sine theta into cos 90 minus phi, that will be sine phi. So the projection of r on the y-axis, we can write r sine theta into sine phi. R sine theta into sine phi. So now we know the projection length of r on the x-axis, on the y-axis, on the z-axis. So we can write the value of x, y, z in terms of r theta phi. So right here from the figure, we can write value of x. What will be the value of x? Is the projection length of r on the x-axis. So from figure we can write this projection length is actually r sine theta cos phi. R sine theta cos phi. Similarly, we can also write the value of y. What is y? Y is the projection of r on the y-axis, and from the figure we have already written here, it will be r sine theta sine phi. So r sine theta sine phi. And what is z? What is the projection of r on the z-axis? That is z. So in this case it will be r cos theta. Okay, r cos theta. So once we know the value of x, y, z in terms of r theta phi, then in next step what we can do, we can write the position vector of p with respect to the origin O. So right here, the position vector of point P with respect to the origin O is Rp is equals to what we can write? We can write x in terms of, if we want to write in terms of x, y, z, then we can write x I cap, y j cap, and z k cap. And how we can write this, that we have already discussed in last class. So once you know the value of Rp in terms of x, y, z, and also we know the value of x, y, z in terms of r theta phi, so we can replace this value of x, y, z in terms of r theta phi. Then we will get the position vector of Rp in terms of r theta phi. So let me write that. So Rp, position vector of P in terms of r theta phi. So we can write, so you have to replace x by this r sine theta cos phi. So what we'll get? We'll get r sine theta cos phi I cap plus r sin theta sin phi j cap plus r cos theta k cap. Okay. So this will be the position vector of point P in terms of spherical polar coordinate r theta phi. Okay. So once we know the position vector of point P in terms of spherical polar coordinate r theta phi, next what we'll do, we will define a unit vector associated with each variable. In last class already told that in any coordinate system, if the position vector is function of n variable, then we can define n number of unit vector associated with each variable. So in this case, in spherical polar coordinate system, as you can see here, this position vector Rp is function of r theta phi. So it's a function of three variable. So we can define three unit vector associated with each variable. So let me define that first. So right here, the unit vector associated with r. Okay. First variable r. So let me write first what are the unit vector associated. What is the unit vector associated with variable r? So usually we represent this unit vector by r cap. And then how we can define this r cap? That's the general definition I have already told in last class. So if we know the position vector in any rectangular, any coordinate system, and if it is a function of n variable, then we can define n number of unit vector. And in spherical polar coordinate, we have noticed that this position vector Rp, let me write here again, Rp equals to, we get r sin theta cos phi I cap plus r sin theta sin phi j cap plus r cos theta k cap. So it's a function of three variable. So we can define three unit vector. So first, we want to define the unit vector associated with variable r. So for that, what we have to do, first we have to take a partial differentiation of this Rp with respect to r, and then we have to divide by its magnitude. Okay, have to divide by its magnitude. So for that, what you have to do, first we have to differentiate, partially differentiate this Rp with respect to r. So when you take differentiation of this Rp with respect to r, keeping theta and phi fixed, what we'll get? We'll get a sin theta cos phi I cap plus sin theta sin phi j cap plus cos theta k cap. And then what we have to do, we have to divide it by its magnitude. We have to divide by its magnitude. What will be the magnitude? It will be under root of x component square, that is sin square theta into cos square phi then y square, it will be sine square theta into sine square phi plus cos square theta, okay, plus cos square theta. So from denominator you can see here, first two term we can take sine square theta common. If we take sine square theta common, what will get? Cos square phi plus sine square phi, that will give you 1. So from first two term we'll get sine square theta, and then in third term we have cos square theta. So sine square theta plus cos square theta, it will be 1. So ultimately this whole denominator will give you 1. So finally we'll get r cap equals to sine theta cos phi I cap plus sine theta sine phi j cap plus cos theta k cap. Okay, cos theta k cap. So this is the mathematical expression of r cap in spherical polar coordinate. In spherical polar coordinate. So this is a unit vector. The magnitude of this unit vector will be 1, and it will give direction, some direction. What will be the direction? We'll see in next phase in a figure. Say in spherical polar coordinate, if we increase the value of r keeping theta and phi, so the directions of increment of r will be given by this unit vector r cap. Okay. Just like in spherical in rectangular coordinate system, I cap give the directions of increment of x, j cap give you directions of increment of y, z cap, k cap give the directions of increment of z. Similarly, this r cap in spherical polar coordinate give you the directions of the increment of directions of, it will give you the directions of increment of r. Okay. Same then the next unit vector, the unit vector associated with next variable, let's say theta. So the unit vector associated with theta. So usually we represent this by theta cap. And how we define it? Just like r cap. First we have to take a partial differentiation of rp with respect to theta, and then we'll divide by its magnitude. Okay. So in order to calculate theta cap, what we have to do? First we have to take the partial differentiation of rp with respect to theta, keeping r and phi fixed. So this is our rp vector. What we have to do? We have to take a partial differentiation of this rp with respect to theta. That's mean we'll differentiate this rp keeping r and phi fixed. So if we do that, what we'll get? We'll get r sine differentiation of sine theta will be cos theta, and then cos phi I cap. In second term, we have again sine theta. So differentiation of sine theta will be cos theta. So this will give you r cos theta sine phi j cap. And third term we have cos theta. So differentiation of this cos will be minus sine theta. So it will be minus r sine theta k cap. Okay, minus r sine theta k cap. Then what we have to do? We have to divide by its magnitude. You have to divide by its magnitude. What will be the magnitude of this vector? It will be r square cos square theta into cos square phi plus r square cos square theta into sin square phi plus r square sin square theta. Okay. So now from first two term, what we can common? We can take common r square cos square theta. So when you take common r square cos square theta, what will get? Cos square phi plus sin square phi. So that will give you 1. So from first two term, what we'll get? We'll get r square cos square theta. In third term, we have r square into sin square theta. So again, if we take r square common, then what will get? Cos square theta plus sin square theta. So that will also give you 1. So finally, we'll get r under root of r square. So whole denominator give you r. In numerator, every term has r. R, R, R. So r from denominator and numerator we can cancel out. And then we'll get theta cap. We'll get theta cap. So what is the value of theta cap? Theta cap is equals to cos theta cos phi I cap plus cos theta sin phi j cap and minus sin theta k cap. Okay. So this is the value of mathematical expression of theta cap in spherical polar coordinate system. Okay. In spherical polar coordinate system. Again, this is a unit vector, so magnitude of this vector will be 1, and the direction, it will give direction. And what will be that direction? It will give the direction of increment of theta. In spherical polar coordinate system, if we want to increase the value of theta, keeping r and phi fixed, so this unit vector give the direction. In along this direction, we can increase the value of theta. Okay. We'll see in figure also after some time. And then we have another variable phi. So let me write the unit vector associated with phi also. The unit vector associated with phi. Unit vector associated with phi. Usually we represent it by phi cap. Phi cap. And how we define it is similar way as we have defined for r cap and theta cap. So first we have to take partial derivative of rp with respect to phi, and then we'll divide by its magnitude. Okay. So you have already written here rp. This is our rp. Now what we have to do, we have to differentiate this rp with respect to phi, keeping r and theta fixed. So when we differentiate this rp, we'll get here minus sin phi, we'll get here cos phi, but this term doesn't have any phi term, so this term will give us 0. So what we'll get here, we'll get a minus r sin theta sin phi I cap plus r sin theta cos phi j cap. Cos phi j cap, then what we have to do, we have to divide by its magnitude. So what will be the magnitude? Magnitude will be r square sine square theta into sine square phi plus coefficient of j cap square. So there is sine theta cos phi. So r square sine square theta into cos square phi. Into cos square phi. So again, take a look on the denominator part. Both the term, from both term we can take r square sine square theta common. So if we take r square sine square theta common, then what we'll get? We'll get sine square phi plus cos square phi. That will give you 1. So finally this denominator will get under root of r square sine theta. And if you take outside of the square root, then we'll get r sine theta. And then also in denominator, see both the term have r sine theta. So r sine theta we can cancel out from denominator and numerator, then we'll get phi cap. So finally what will be the value of phi cap? Phi cap will be minus sine phi I cap plus cos phi j cap. Okay, plus cos phi j cap. So these are the 3 unit vector associated with 3 variable. Okay, so if we know the value of, you can see here, r cap is function of theta phi, theta cap is also function of theta phi, and phi cap is function of phi. And one more thing you can notice here, r cap is in general function of I cap, j cap, k cap. So r cap have 3 component, I component, j component, k component. So usually r cap will lies in the space because it has 3 component. Similarly, theta cap is also has 3 component, I component, j component, k component. So it will also lie in space. But if you take a look on phi cap, it has only I component and j component. It doesn't have any z component. That's when this phi cap will always lies in the xy plane. Always lies in the xy plane. So from this mathematical expression, if we know this mathematical expression, from this mathematical expression we can find out what will be the directions of r cap, phi cap and theta cap at any position on the surface of a sphere. But what I believe that when you're going to solve some problem in electrostatics or electrodynamics, sometimes should visualize the directions of r cap, theta cap, phi cap figure. If you can understood that which directions is r cap represent, which directions theta cap represent, which directions phi cap represent, then sometimes it will be very easy to solve the problem actually. So for that, let me draw a sphere here again. Let's assume that it is a sphere. And let's say this is z-axis, this is y-axis, and this is x-axis. And this is the origin of the rectangular coordinate system, as well as it is also the center of the sphere. Okay, it's also center of the sphere. Then let's say this is x-axis, this is y-axis, and this is z-axis. So the way we have defined r, theta and phi. So if I want to ask you what will be the value of theta and phi at this point, what will be the value of theta and phi at this point? So at this point, if we connect this point with the origin O, so it will be parallel to the x-axis. So if it is parallel to the x-axis, then what will be the angle between this r and z-axis? It will be 90 degree. So that's mean theta will be 90. Value of theta will be 90. And let's say radius of the sphere is r. Radius of the sphere is r. So from the distance, so the distance of this point from the center will be r, because this point is on the surface of the sphere. So r, and then theta is pi by 2. And what will be the value of phi? So phi usually make the projection of this r and on the positive x-axis. In this case, since the r vector is parallel to the x-axis, lies on the x-axis, so if we take projection on the x-axis, projection on this r, it will also be on the parallel to the x-axis. So in this case, phi will be 0. So for this point, phi will be 0. Now what about this point? Again, this is on the surface of the sphere, so r will remain capital R. What will be the value of theta? Again, if you join this point with the origin, so this will also lie on the y-axis, so it will make an angle with the z-axis 90. So theta in this case, it will also be 90. And what will be the value of phi here? So now this vector makes an angle 90 with the positive x-axis. Positive x-axis. So in this case, phi will also be 90. Okay, phi will also be 90. Now let me define the directions of r cap, theta cap, phi cap at these 2 points. Then we can generalize what will be the value, what will be the directions of r cap at any point on the surface of the sphere, and what will be the value of theta cap, and what will be the value of phi cap. Okay. So for that, what we have to do at this point, we have noticed that the r cap, theta cap, phi cap, they are actually function of theta and phi only. You see, r cap is function of theta and phi. Theta cap is also function of theta and phi cap is function of phi. So once you have this r cap, theta cap, phi cap in terms of r, theta, phi, and you know the value of theta and phi at this point, so just what you have to do, you have to put the value of theta is equals to 90 degree, phi equals to 0 degree for this point, and what will get, what will get the value of r cap, theta cap, phi cap. So if you write this theta cap equals to pi by 2 and phi cap equals to 0 into r cap, what you will get? Theta equals to 90 and phi equals to 0. So if you put here theta equals to 90, phi equals to 0, first term will give you 1, so 1 I cap. Second term, sine phi here, so phi equals to 0, this will give you 0. And then cos theta, theta equals to 90, cos theta will be 0. So r cap will be I cap. Okay, r cap will be I cap. Then what will be the value of theta cap? So for that, again, you have to put theta equals to 90 and phi equals to 0 in this equation. So what we'll get? We'll get, when you put theta equals to 90, this term will give you 0. When you put theta equals to 90, this term will also give you 0. But when you put theta equals to 90, this term give you minus k cap. So here theta cap will be minus k cap. Okay, minus k cap. And what will be the value of phi cap? What will be the value of phi cap? So for that, we have to put the value phi equals to 0 in this equation. in this equation. So if you put phi equals to 0, what will get? Sine phi is equals to 0, sine phi 0 0, and then cos phi 0, cos 0 is give you 1, so it will give you phi cap equals to j cap. Phi cap equals to j cap. So you know the r cap, you know the value of theta cap, you know the value of phi cap. So now you can draw the directions of r cap, theta cap, phi cap in this figure. So r cap will be in this direction, positive x-axis at this point. R cap will be along this direction. So this is the directions of r cap. And then if z is upward, then minus k cap, that is minus z cap direction, so it will be downward. So z cap, theta cap will be this direction, in this direction. So directions of theta cap. And what will be the directions of phi cap? Phi cap will be positive y-axis, so it will be along this direction. It will be along this direction, phi cap. Okay. Now same way, you can write the value of unit vector r cap, theta cap, phi cap for this point. For this point. So when you put these three equations in r cap, the value of theta equals to 90 and phi equals to 90, what we'll get? We'll get r cap equals to plus j cap. R cap equals to plus j cap. And then if you put a value of theta and phi 90 90 in phi cap, what you'll get? We'll get again minus k cap. Minus k cap. And what will be the value of phi cap? So when you put value theta equals to pi by 2 and phi equals to pi by 2, we'll get here minus I cap. Okay, minus I cap. Okay, phi cap equals to minus I cap. So again, if you want to draw here r cap, theta cap, phi cap out here, so r cap will be in this direction. This is the r cap. Theta will be downward in this direction. This will be the theta cap. And phi cap will be minus I cap. So this x-axis in this figure, we can say it is out of the page. So phi cap, it will be into the page. So you can draw like this circle with a cross, that will give you phi cap at this point, means into the page. Okay, into the page. So r cap, theta cap, phi cap, you can see here. So in this 2 point, we have calculated the value of r cap and theta cap. For this point, r cap is positive I cap direction, and from with the center, with respect to center, if we see, it will be always radially outward. Here you also see it is positive. When you take the point on the positive y-axis, the directions of r cap actually j cap. So again, it's with respect to center, if you notice this point, it will be always radially outward. So r cap will be always radially outward. And then for theta cap, what we can generalize this way, theta cap will be, let's say this is the north pole of this sphere, and this is the south pole of this sphere. So if we draw a semicircle from north pole to south pole like this, north pole to south pole. If we draw a semicircle on a sphere from north pole to south pole, taking the center of the sphere as a center of the semicircle, and then if we draw the tangent on this circle at any point from north pole to south pole, in the direction north pole to south pole, that tangent actually give you the directions of theta cap. So any point, at this point, if we want to draw the value of theta cap, what will be the direction? So this is the north pole, this is the south pole. So in the sense, what what we have to do, you have to draw a tangent in the directions of south pole to north pole. So what you have to do, you have to do it like this. If we draw a tangent this direction, it will be like this. This will be the directions of theta cap at this point. If we want to draw the directions of theta cap, again we have to draw a tangent on this circle from north to south. So it will be like this, not like this, like this. So this will be the directions of theta cap at any point on the sphere. Okay. So if we ask what will be the directions of theta cap at any point on the sphere, what you have to do, you have to draw a circle, semicircle from north pole to south pole through this point. Let's say if I consider another point here. But here, what you have to do, you have to draw a semicircle from north pole to south pole through this point like this. And then what you have to do, you have to draw a tangent from north pole to south pole. From north pole to towards south pole. So at any point, if we want to draw like this, tangent like this, so this will give you the directions of theta cap at this point. Okay. So now what will be the directions of phi cap? What will be directions of phi cap? So for that, you can see here, for this position, for this point, when we take a point on the x-axis, but we have noticed that the directions of phi cap is positive y-axis. And when we took another point on the y-axis, what we have noticed that the directions of phi cap is minus y-axis. So from these 2 points, we can say that it is actually phi cap will be the tangent. It will give you, if you draw a tangent in anti-clockwise direction on this circle, on this circle. This is also circle about the z-axis. So on this circle, if we draw a tangent in anti-clockwise direction, then the tangent of this directions of this tangent will give you the directions of phi cap at any point. If I want to draw the value of directions of phi cap at this point, then what we have to do, about the z-axis, we have to draw a circle which will passes through this point. So we can draw like this, and then what we have to do, we have to draw a tangent on this circle in anti-clockwise direction. So in this direction we'll draw. So if we draw a tangent like this, so this will be the directions of phi cap. This will be the directions of phi cap. This will be the directions of theta cap. And what will be the directions of r cap? R cap will be always radially outward. Okay. So let me summarize this again. So r cap will be always radial outward. For theta cap, phi cap, what we have to do? For theta cap, we have to draw a semicircle from north pole to south pole, passes through this point, and then we have to draw a tangent on this semicircle from north to south. And the directions of this tangent will give you the directions of theta cap. And for phi cap, what we have to do? We have to draw a circle about the z-axis which will passes through this point, and then if we draw a tangent on the circle in anti-clockwise direction, and that will give you the directions of phi cap. Okay, so if you remember this thing, I think you can find out the directions of theta cap, phi cap at any point on this surface of a sphere. Okay, surface of a sphere. Good. Then next thing, what we have to remember, one more thing here. Now we have already written here r cap, theta cap, phi cap. So you can do a homework. Just take the dot product r cap with theta cap, or say theta cap with phi cap, or take the dot product with r cap. All the cases you will get actually 0. All the cases you will get 0. So that's mean this r cap, theta cap, phi cap, they all are unit vector, but they are a mutual dot product is 0. That's mean they will be always mutually perpendicular with each other. R cap, theta cap, phi cap, they will be mutually perpendicular with each other. And also we can, from this figure also we can see here. See, in this I cap, j cap, k cap, they all are perpendicular with each other. And second thing, if we write this way, R cap, theta cap, and phi cap. That's mean if we take a cross product, R cap with theta cap, that will give you phi cap. And if you take a cross product theta cap with phi cap, that will give you R cap. And if you take a cross product phi cap with R cap, that will give you theta cap. But if you reverse this cycle, if you take a cross product theta with R, that will give you minus phi cap. If you take a cross product R with phi, that will give you theta cap. And if you take a phi cap, cross product of phi cap with theta, that will give you minus R cap. Minus R cap. Okay. So remember these two things. When you take cross product R cap with theta cap, that will give you phi cap. And when you take cross product theta cap with phi cap, that will give you plus R cap. And if you take cross product phi cap with R cap, that will give you theta cap. But if you reverse this cycle, if you take cross product theta cross R, that will give you minus phi cap. Similarly, if you reverse this one, phi cross theta, that will give you minus R cap. And if you take cross product R cross phi, that will give you minus theta cap. Okay. So this is the direction, and we have already calculated the mathematical expression of theta cap R cap. And also we have seen in this figure what are the directions of R cap, theta cap, and phi cap. Now, once we know this R cap, theta cap, phi cap, directions of R cap, theta cap, phi cap, we can define few parameters. Look at this. This is first is elementary length in spherical polar coordinate system. Elementary length vector in spherical polar coordinate system. Okay. So we have defined unit vector. We know the directions of R cap, theta cap, phi cap. And now what we are going to say, what we are going to do here, we are going to calculate the value of elementary length. What is the concept of elementary length? That we have already discussed in rectangular coordinate system. If we have a large length, sometimes it is necessary to divide it, break down this large length into small length. Smallest possible length is called elementary length. Now, if we represent the smallest possible length in rectangular coordinate system, we know how to represent dl equals to dx I cap, dy j cap, dz k cap. So same way, if we want to define this elementary length in spherical polar coordinate system, then what will be that length? So for that, let me just define first elementary length along r, theta, phi, and then we can write them together. That will give the elementary length. So for that, let me draw here two concentric sphere. Two concentric sphere. Let's say this is the inner sphere, and it has radius r. And also consider another concentric sphere, and let's say it has a radius r plus dr. R plus dr. Now, what is dr? Let me first define that dr. So assume that this whole universe is spherical. What we are assuming? We are assuming that this whole universe is spherical. How we want to represent this universe by this spherical polar coordinate system? So for that, what will be the value of, what will be the limiting value of r? It will be 0 to infinite. 0 to infinite. So it's very large. So now if we want to increase the value of r, so we can increase the value step by step. So the smallest possible increment of r is represented by dr. Smallest possible increment of r is represented by dr. Okay. Now, what I am asking you, let's say you are at this point, you are at this point, at any point on the surface of the inner sphere. Any point on the surface of the inner sphere. Now, if I ask you how much distance you have to travel to go from inner sphere to outer sphere along the directions of r cap. R cap means radial outward. That we have already noticed here. R cap will be always radially outward. Radially outward. So if I ask you, let's say you are here, you want to go from inner sphere to outer sphere along the r cap, means you have to go along this path. So what will be this length? This will be dr. Let's say you are here, again you have to go radially outward, so you will go this distance. What will be that distance? That distance will also be dr. Everywhere, if you want to go inner sphere to outer sphere along the r cap, this distance will be dr. And what is dr? Dr is the smallest possible increment of r. So that's why we write the elemental length along r is dr r cap. And in general, we represent as dl r. R component of elementary length in spherical polar coordinates. So what we'll write? We'll write dr r cap. Dr r cap. Magnitude is dr, and r cap will be the radially arc outward direction. Okay. Now next what we have to do? We have to define. Now we have defined elemental length along theta cap. Elemental length along theta cap. So for that, what we have to do? Let me draw a sphere again here. Let's say this is a sphere. And let's say this is the z-axis. Okay, this is the z-axis. Now consider a point on this sphere making an angle theta with the z-axis. Okay, theta with the z-axis. Now keeping the value of r and phi fixed, if we want to increase the value of theta, so when you take this point on the z-axis, theta will be 0 because we are measuring this theta with respect to z-axis. So if you take this point on the z-axis, then it will be 0. If you come here, then theta will increase, theta will increase, theta will increase. So if we increase this value of theta by a small angle d theta, keeping r and phi fixed, then what will happen? This point will shift at this point, along this line, along this semicircle. So if this angle is d theta and the radius of the sphere, let's say r, then this length, see, this will be the elemental length. When d theta is very, very small, so this length will also be very, very small. So this length is called elemental length. And what is d theta? D theta, again, if you want to represent this whole universe according to spherical polar coordinate system, then what we have to do? We have to increase the value of theta from here to here. From first here, then we'll take here, then we'll take here, then we'll take here. So if we take point here, here, finally we'll reach at this point. So in this case, the value of theta will be, limiting value of theta will be 0 to pi. 0 to pi. So again, between 0 to pi, we can increase the value of theta by step. So the smallest possible increment of theta is represented by d theta. So this d theta will be very, very small. So if this d theta is very, very small, then this length will also be very, very small. And from this figure, we can write what will be this length. This length will be r d theta. R d theta. Now if I ask you in which direction this length will generate, theta cap, phi cap, r cap. So you see, if we draw a tangent, so it will be tangent on the semicircle, on this point to this point. If we draw a semicircle through this point, this will be the semicircle. So on this semicircle, I am drawing a tangent on this point from north pole to south pole, and along this direction, this elementary length is generated. So that's mean this elemental length will be along theta cap. This is the directions of theta cap. So that's why this elemental length is written elemental length along theta will represent a dl theta. So dl theta is equals to r d theta, and directions will be theta cap. Okay, directions will be theta cap. And then finally we have to define one more length, that is phi cap, elemental length along phi cap. So for that, again, let me draw a sphere first. Let's say this is a sphere, and the z-axis, the y-axis, this is the x-axis, z-axis and x-axis and y-axis. Now what I'm doing here, let me just consider a point inside the sphere at a distance r from the center, making an angle theta with the positive z-axis. And if we take the projection on this r on the xy plane, this projection will be, this projection, let's say, make an angle phi with the positive x-axis. So we can represent this point according to spherical polar coordinate by r theta phi. Okay, r theta phi. Now let me draw a circle about the z-axis which will passes through this point. So what we have to do, let's say this is the radius of the circle. So consider taking this as a radius. So about z-axis, if we draw a circle, so circle will be like this. Circle will look like this. So now, keeping the value of theta and r fixed, keeping the value of theta and r fixed, if I change the value of phi, then this point actually will move along this circle. This point will move along on the circle. So now if I increase the value of phi by a small angle d phi, then what will going to happen here? Then this point actually will shift from here to here. Okay. We increase the value of phi, keeping the r and theta fixed, then this point will shift from here to here. This is this point, and this is the another point. So if we take the projection, then this will be the projection length, the xy plane. So this angle is phi, d phi. This angle is d phi. So if this angle is d phi, then what will be this length? What will be this length? So let me just clear this picture a little bit more. This is the first point, and then I have increased the value of phi by a small angle d phi, and because of that this point has shifted from this point to this point. Now this angle is d phi. This angle is d phi, and what will be the value of this radius of this circle? From this figure you can see, from this point we have drawn a perpendicular on the z-axis. So if this angle is theta, then we have taken projection on the z-axis will be r cos theta. So what will be this length? This will be the projection length actually, r sin theta. So the circle we have drawn here, it has radius actually r sin theta. Now if this circle has radius r sin theta, then if this angle is d phi, then what will be the distance between these 2 points? This length will be r sin theta d phi. R sin theta d phi. And which directions this length will generate? This will be the directions of phi cap. I told you, if we draw a circle and then if we draw a tangent at any point on this circle in anti-clockwise directions, that will give you the directions of phi cap. So this length will also generate in phi cap direction. So that's why it is called dl phi cap, and this is the elementary length along phi cap. Okay, so dl phi. So now we have component r cap, dlr, dl phi, dl theta, dl phi. So we can write elementary length in spherical polar coordinate, and that will be dl. So dl will be dlr, that is dr r cap, plus r d theta theta cap, plus r sin theta d phi phi cap. Okay, plus r sin theta d phi phi cap. So this will be the elementary length in spherical polar coordinate system, total elementary length. And if I want to write the elementary length along r cap, then what we'll write? We'll write dr r cap. If we want to write elementary length along theta cap, what we'll write? We'll write r d theta theta cap. If we want to write elementary length along phi cap, then what we'll write? We'll write r sin theta d phi phi cap. Okay, r sin theta d phi phi cap. Okay. Now once we know this elementary length, what we can define? We can define elementary vector. Elementary vector. So elementary area vector, not elementary vector. Elementary area vector. So what is the concept of elementary area vector? So we know that if we have a sphere of radius r, let's say this is a sphere of radius r, then we know what will be the total area, total surface area, curved surface area, sphere will be 4 pi r square. Now the r has a large value, then this area will be very, very large. So now we want to divide this large area into small area, and then smallest possible area, we want to write the smallest possible area in spherical polar coordinate system. We have already noticed that how to write this elementary area in rectangular coordinate system, in 2D polar coordinate system. Now we want to write this elementary area in spherical polar coordinate system, and this is very, very important because after some times we will going to solve Gauss law. Using Gauss law, we have to calculate electric field, electric flux. So for that, every time if it is related to the spherical surface, then every time we have to consider this elementary length on the spherical surface. So for that we have to first we have to learn how to write this elementary length on a spherical surface. For that, let me just draw a sphere again. Let's say this is a sphere. This doesn't look like sphere. So let's say this is a sphere, and then consider, let's say this is y-axis, this is x-axis, and this is z-axis. Okay, x-axis, y-axis, and z-axis. Now what we have to do, let's consider a point on this. This is a sphere of, let's say, radius r. Let me draw this circle also. So this is sphere of radius r, and on the curved surface of the sphere, let's consider a point P. This is a point P which is lies on the curved surface. That's mean if I draw this point by a semicircle, so this will lies on here. And also let me draw another circle around the z-axis which will passes through this point. Like this. Okay. And let's say this angle is theta, and if we take projection of this length, this r, this will make a phi angle with the positive x-axis. So the coordinate of this point will be r, phi, and r theta and phi. Okay, r theta and phi. Okay, r theta and phi. Now since it is on the curved surface, so from the center to, if we consider sphere, and the distance between any point on the surface and center of the sphere will always remain same, and that will be the radius of the sphere. Okay, but if we goes from one point to another point, then this theta and phi actually will change point to point. If we consider a point here, then theta will be 0 and phi will be depending upon, yeah, this is actually a, what we can say, we cannot define the value of phi here. I can have many values here. So let's consider another point here. Then we can define the value of theta is 90 and phi will be 90. If we consider another point here, then theta will be 90 and phi will be 0. So if we goes from one point to another point on the curved surface of a sphere of radius r, then theta and phi will change. Okay. So in the same way, if we consider, let's say this is the P point. Now what I am going to ask you, I'm asking you that if we are keeping the value of phi and r fixed, if we increase the value of theta by a small angle d theta, this point will shifted along this line or this line. What I am asking you, I ask you that if the value of r and phi fixed, and if we increase the value of theta by a small angle d theta, then this point will move on the red line or on the white line. it will move on the white line. Because phi is fixed, this means this point will always makes the same angle. If we take the projection of this r, it will always make the same angle with the positive x-axis. So this will supposed to move along this white line. So keeping the value of theta, phi and r fixed, if we increase the value of theta by a small angle d theta, then this point actually shift here to here. If this angle is d theta, then this point will shift from here to here. Okay. And then again come back at this point. Now increase the value of phi by a small angle d phi. Small angle d phi. At that time, this point will shift along the red line from here to here. So if this angle is d phi, then this point will shift from here to here, and this length will be r sine theta d phi. This is the elementary length along phi cap, and this will be the elementary length along theta cap. Okay, along theta cap. And just for completeness at this moment, write this radius of the sphere, not capital R, let's consider it smaller. Okay, consider smaller. Radius of the sphere is smaller, and then we have considered one point on the sphere whose coordinate is r theta phi. Then what we have did, we have increased the value of theta by a small angle d theta. Then this point will shift along this line, and this length will be r d theta. And when you increase the value of phi by an angle d phi, making theta keeping theta and r fixed, then this point will shift from here to here. So this length will be r sine theta d phi. So now if we draw a parallel line of this line, and if we draw a parallel line of this line, this will give you elementary length on the curved surface of the sphere, elementary area on the curved surface of the sphere. Curved surface of the sphere. This area, if we put this area side by side over the curved surface, and finally we'll get actually big surface. So this is called the elementary area. This is called the elementary area. So what will be this area? One side of this area is r d theta. Another side length is r sine theta d phi. So this area will be product of these two lengths. It will be r square sine theta d theta d phi. R square sine theta d theta d phi. That will be the elementary length in spherical polar coordinate, elementary area on the curved surface of a sphere. So ds, what will be the magnitude of ds? It will be r square sine theta d theta d phi. Now this is an elementary area vector, so it will have some direction. It will have some direction. What will be the direction? So what we have to do, consider you are inside the sphere and you want to draw a normal, outward normal. So sphere is a closed surface. So now calculate to draw the directions of area vector. What we have to do, we have to draw an outward normal at any point on the surface. So we want to see the directions of area vector at this point. So what we have to do, we have to draw a outward normal at this point. So if we draw a outward normal, so you imagine you are inside the sphere and you want to draw a outward normal at any point on the spherical surface. Which directions it will be? It will be along r cap, radial outward, r cap direction. It will be along r cap direction. So in this case, this will be r cap. So in spherical polar coordinate system, we want to write the directions of area vector, value of elementary area vector. What we'll write? We'll write r square sine theta d theta d phi r cap. R square sine theta d theta d phi r cap. Okay. And now what will be the elementary volume? So for elementary volume, let me just draw this part only. So this is z-axis, this is y-axis, this is x-axis, and imagine that whole universe is spherical. So we want to represent this whole universe by this spherical polar coordinate system. So it will be very large volume. Now we want to break down this large volume into small volume, and what will be that possible smallest volume in spherical polar coordinate system. So for that, what we have to do, what I am doing here, I am just drawing this area, this portion again here. This portion only. This was this portion now. Now what we have to do, so when you consider only a sphere, sphere of radius r, that time r will be fixed on the curved surface. If you on the curved surface on a sphere, if you go any point from here to here at any point on the surface, always the distance between these points will be remain same. But if you goes from one sphere to another sphere, then this r will also change. So in this case, we have to multiply. This is the base area, and if we multiply the height, that is the elementary length along r cap, elementary length along r cap, that will give us actually this portion. This is a cubic portion. This cuboid portion. That cuboid portion give us the volume of elementary volume in spherical polar coordinate system. This will give the volume of this cuboid, give the elementary volume in spherical polar coordinate system. So for that, what we are doing here, we have done here, we have increased the value of r by dr. So this length is dr. Okay. And what is the base area? Base area already we have written here, r square sine theta d theta d phi. So this area is r square sine theta d theta d phi. So now if we multiply with dr, that will give the volume of this cuboid, and that will be the elementary volume in spherical polar coordinate system. So elementary volume in spherical polar coordinate system. And what will be that elementary volume? dV equals to this base area into this height. So it will give you r square sine theta dr d theta d phi. Okay. This will be the elementary volume, r square sine theta dr d theta d phi. Okay. What will be the area? R square sine theta d theta d phi. And what will be the volume? R square sine theta dr d theta d phi. Dr d theta d phi. Now we have to write the limit of r theta phi. So what will be the limit? So if we represent this universe by spherical polar coordinate system, and the center of the universe lies at the center of the coordinate system, then it will be the limit of r will be 0 to infinite. 0 to infinite. And then what will be the value of theta? So first we have to take, if we draw a sphere, if we want to draw a sphere, how we can draw a sphere or make a sphere? For that you can see this logic. Let's say this is x-axis, y-axis, z-axis. So first what to do, we can consider a point on the z-axis at a distance r. And then we have to make, if we rotate this point around the z-axis by an angle 2 pi, it will remain at the same point. Now consider another point making some angle with the z-axis, let's say angle theta. And then if we rotate this point about the z-axis by 2 pi, and the path it will follow, if we connect this point, what we'll get a circle around the z-axis like this. And then if we increase the value of theta again, but the distance still r, keeping the distance fixed, then we'll get a circle like this. And then again we increase the value of theta this direction, this will give you circle like this. And then finally we can take another point on the negative z-axis, and if we rotate about the z-axis by 2 pi, this will give you point. So if we connect this whole point, this will give you actually a sphere. This will give you a sphere. So to form a sphere, what we have to do? First we have to fix the value r. So in this case, if it is whole universe, then we have to, the value of r will be 0 to infinite. And for theta, what will first we have first point we have taken on the positive z-axis. So the angle between this r and the z-axis will be 0. And then we have increase. Finally we have taken a point on the negative z-axis. So if we connect this point with the origin, so this will be the maximum value of theta. So limit of theta will be 0 to pi. And then what will be the limit of pi? For each value of theta, let's say each value of theta and r, what we are doing to make this, we are actually in a circle around the z-axis. So to make this circle, we have to rotate this point by an angle 2 pi. So that's the limit of phi, that is 0 to 2 pi. So limit of phi will be 0 to 2 pi. Yeah. So I think if you know this concept related to the spherical polar coordinate system, that will be enough to understand the electrodynamics or to solve different type of problem related to the spherical shape. So I think this will be enough for today's class. In next class we will talk about this cylindrical coordinate system. So let's stop here today. See you in the next class, and thank you for watching.